Hello. My name is Ray Harrison. I'm here with my colleague, PRASHANT KHANOLKAR. We are from Comcast. A lot of news about Comcast these days, of course, so we're tracking all of that. We're here to talk about data science pipelines for real companies. And it's a bit of a cheeky phrase, I guess, but our goal there is to say, we're not Uber, we're not a startup, and that we have a lot of use cases and things that have to do with being a legacy company or an older company or however you want to call it, but we have data and processes and things that can literally go back decades for us. And everybody here, your companies are doing machine learning in one way, shape, or form, right? So it was thinking back to the keynote from yesterday, sort of on that AI ramp. And if you've seen any of our talks over the last few years, you've sort of come with us on our data journey, that we've talked about a lot, where we are focused on, first, corralling all of that data, putting some governance. We talked a lot about governance and security last year, and this year we're talking a lot about how we use it, and machine learning is one of those key areas. And interestingly, there are products that are coming out around machine learning pipelines, but everybody's company is different, and how you use those tools is going to be different as well. So for us, let's talk a little bit about Comcast. We are a media and entertainment company. We have a lot of lines of business. Those lines of business generate a tremendous amount of data. Some of the data that we talk about today is just the tip of the iceberg. So everything from high-speed internet, we run our own plant. We're one of the largest ISPs around. But video and content delivery to our newest Xfinity mobile. We did about $84 billion in revenue in 2017, and we have 29 to 30 million customer relationships. And those customer relationships are very, very important, as I'm sure they are to your companies. And that's where we focus a lot of our machine learning and our expertise. PRASHANT and I are not data scientists, so you're not going to get any algorithms and frameworks and stuff from us. But we're data experts, and we're part of a new data vertical at Comcast called the Data Experience Team, or DX for short. And it's a mandate from our executive leadership of, hey, data matters, right? So we all know data matters, but having that come in from our executive team has been critical to some of the work that we've done to take some of this stuff forward. PRASHANT and I are from Colorado, so depending on, we like this view ourselves, but that's sort of depends on where you come from, I guess. So our background, like many so-called real companies, we have a lot of vendors. We've got a tremendous amount of data. We have our 30 million customers. Those customers have devices at their homes. They have that are owned by Comcast, but they also have their iPhones and tablets, smart devices, smart home components that are generating a lot of data at the edge. So we're bringing in tremendous amount of data at the edge. We have within our ecosystem roughly 80 petabytes of data. That's really just the tip of the iceberg too. There's a lot that we haven't tapped into yet. We have a lot of organizations at Comcast. All of them are very interested in gaining insight into all of this data, with our streaming data and click events and our billing relationships. So a lot of interest in the data, and as part of this DX organization, as part of this data vertical, we are laser focused on providing that insight. The data science folks in various organizations within Comcast use a lot of different tools. This is just some of them. And so again, we're not really about what framework is getting used. We're not really about particular algorithms here, but we are focused on access to and really providing the information about data so that data scientists can get to it. So we need a data science pipeline, and we need an enterprise data science pipeline, because a data scientist that sits in a corner office somewhere that's generating insight that somebody else doesn't know about but could maybe use really is wasted effort. It's not very valuable to the company always. So that's kind of the goal here with what we're trying to do is provide, as part of this DX organization, providing access across all of these disparate data sets. I keep, and for a reason, I keep mentioning this concept of a data vertical. And let me just throw this up here. We're always doing something like this as part of a data science pipeline, and people are familiar with this flow. It's pretty standard. It may be different where you are. You may have other things that you do, but relatively, feature engineering, training, deployment, and so forth. But data vertical is one of our 5 pillars of success. So if you can take away anything from what we talk about today, it's sort of these 5 things. And your data being a first-class citizen, doing what you can to get executive acknowledgement of that, and it won't take much these days, right? But it's critical. We have data in the cloud. We have a lot of data on-prem. That data is in Hortonworks, HDFS, Hadoop clusters. It's in a lot of relational databases. It's in probably people's laptops and Excel spreadsheets. Lots of data, right? And on-prem, it's in the cloud. Our goal and our mandate is federation of that data. So with federation, it's really important to have information about how good that data is. So if you saw Barb Ekman's talk yesterday, we're really deep into metadata. So we're using Atlas and some other tools to drive, help drive lineage, help drive insight into all of our multiple data sets that we've got laying around. So data science, you hear a lot of common phrases, features, models, things about the various algorithms, hyperparameters, and so forth. What we found is that there are nuanced behavior definitions of those things, depending on who you're talking to. And so what we do is we work with a lot of our data science teams to really drive that common vocabulary. So sort of that semantic, in a way, a semantic layer of language around how we talk about machine learning, how we talk about data science, and ultimately how we talk about AI. It's no good if you can't find it, sort of goes without saying, but again, it's really our focus on metadata that's driving that. So not only do we want to know where data sets are, we also want to know where features are, and what are metrics around those features, what are metrics around those models. And then a common way to do production releases of models. That's an area that we're starting to focus on, but it's really critical, I think, to those to success. So having the ability for everyone to come in and understand where endpoints are and how to go do and utilize the predictive services. It's all about metadata. I'll say it one more time. So that's kind of where we're going to focus. I'm going to turn it over to Prashant now, and he's going to walk us through some where we are today, right, and take us through some customer experience machine learning and some really interesting use cases there. And then I'm going to come back and talk a little bit more about where we are with metadata, and then where we're going with taking a look at how we can. Our goal really is to make sure that we have tools for data scientists to use so that they can discover things and so that they can share the work that they're doing, be it with other data scientists or with executives, and make sure that we're elevating what they do to ensure that value is driven into the organization. So that's really where we're focused. We do a lot of very interesting machine learning and AI and data science at Comcast, and Prashant is going to talk to you about one of the groups that we work with that does some really interesting things. So Prashant, over to you.
Thanks, Ray. So a little bit about machine learning and applied AI at Comcast. At Comcast, we are a very data-focused organization. We want to use that data to derive insights to improve the customer experience. AI is pervasive. It's being used across all areas of Comcast, such as the X1 video platform, high-speed internet. We even use it in our universal theme parks for managing crowds efficiently. So we have the use cases out here. I'm going to quickly go into a few key use cases, which is using AI for content discovery, using AI for customer service, and using AI for self-service. So let's look at the content discovery scenario. That's our X1 Xfinity voice remote. It actually won an Emmy Award in 2017 for contextual voice navigation and for discovering and interacting with TV content. But that award really is a testament to the innovative platform that provides the metadata and the data, and it powers that Xfinity voice remote. We have delivered more than 18 million of these voice remotes to our customers so far, and the customers love them so much that in December 2017 alone, they delivered more than 500 million voice commands, right? And you can talk to your remote various things such as, simple things such as changing a channel, asking for a particular artist, recording a show. So those were easy intents which are mapped to certain keywords or God words, and we've gone from our very beginning to more semantic search, so more advanced search capabilities. So now we can use things like show me the episode of Seinfeld where George becomes a marine biologist. So we've gone from the old T9 search, which is using your cursor to just move it across the screen, and to just deep voice. So that's the evolution of intents with the Xfinity voice remote. We can say show movies about Scotland, and we are using the same platform to derive intents for our Xfinity Home product to secure your home. So you can ask questions such as, did this package get delivered, or show me who came at my door between 6 p.m. and 9 p.m., and it can figure out those intents and take appropriate actions. Here's an example of AI for customer service. Let's say you're having an issue. You call up a customer service agent. We deploy intelligent services out there in the field to help the agent get to a resolution as quickly and efficiently as possible, getting the device telemetry, running the models in real time, and coming up with the prescriptive actions. So we want to go from reactive to predictive to proactive. That's the ideal situation out there, that we are doing the real-time telemetry, fault isolation, and correlation, and we can predict the problem even before they become evident to the customer, and probably send a tech, or the best thing is we could self-heal. So here is the Xfinity virtual assistant. It's within the My Account app. So if you're not familiar with the My Account app, it's an app available on Android or iOS, which you can use to get an overview of all of your products and services with Comcast, see how they are doing. You can ask questions like, show me my bill. You can use it to pay your bill. And let's say if you're having a customer service issue that we haven't surfaced before, you can use it to type a question, and such as, hey, I'm having slow internet, or I'm having an internet problem. And let me kind of double click into that use case as to how the virtual assistant works. So we solicit natural language input from the customer who says, I'm having an issue with my internet. We pass it through our NLP mechanisms. At the same time, we are pulling the domain models, which are specific to that particular customer intent. We are also getting the device telemetry from all of the devices in your home, and also finding out what's happening in your neighborhood. We run it through our predictive AI and ML algorithms. We try to figure out what's the root cause problem. We pass it through a decision engine, and we present an action catalog to the customer, which could be notifying him or her back on their device, their iPhone or Android device, getting them in touch with a customer care agent, maybe scheduling a truck roll, or the best situation is we are able to self-heal. So the Comcast AI platform, even though it's kind of laser focused on providing the customer the best service, I wanted to say that we also are focused on avoiding truck rolls, because truck rolls are very expensive. Comcast literally has the 5th largest commercial fleet in the US. We have more than 35,000 trucks, which are very expensive. So if we can avoid a truck roll and solve an issue by either self-healing or rebooting a device, we like to avoid those truck rolls where we can. And here is a small example of the virtual assistant intent classification. So we can get a variety of inputs from the customer, which we map to specific intents. And this is a very simple example, but we're doing many more interesting things than that. But this is just mapping a customer query to an intent, saying, hey, I have questions about my bill. So the intent becomes billing. When will my internet be restored? So we figure out that has to do with the internet, and so on. And here is a simple example of the intent classification with deep learning. A customer types the query, I'm having trouble with my internet. We will tokenize it. We'll use the word embeddings, pass it through our recurrent neural networks to find out that, hey, we're talking about an internet issue. And if you change just one word, I'm having trouble with internet speed, now that changes the intent completely, saying I'm going from an internet issue, maybe my internet is down, to an internet slow speed. And here is an example of how the training happens. So we are getting the device telemetry from the devices in the home. We have established event streams to get all this data and corral all this data and land them into our online or historical feature stores. And we run the supervised learning models offline on that data. Pass it through a decision engine, and then present an action catalog, and back to the customer. So this is a loop. So we go from answering questions to questioning answers, and refining our models. And I'm not a data scientist, so I'm not going to pretend that I am, but this is kind of the general flow. Here's a reinforcement learning use case issue. Let's say the internet quality drops every Saturday at 6 p.m., and the action that we prescribed is to reboot the box. And we do that a few times, and the machine learning algorithm now needs to learn that rebooting the box is unlikely to help. So after a couple of times, the reinforcement mechanisms need to understand that the reboot action is not helping, so the reward prediction is low. Here's an example of a space correlation issue. We rolled 3 trucks when 1 was enough. The machine learning algorithm needs to understand that there is no need to send 3 repaired trucks. The geolocation is in the context, so we need to find out, based on the clustering algorithm, saying, the likely failure is just isolated to a single point. So here are some of the technical challenges that we face with our data science platform and building these machine learning pipelines. One of the problems was we have multiple programming and data science environments. We have widespread and discordant data sources. Comcast is kind of a legacy company. We have inherited a lot of data. We have lots of legacy data platforms, Oracle, Teradata, and so on. And then, more recently, Hadoop on-prem and in the cloud. We have multiple machine learning frameworks in use. People are using Databricks, Spark, H2O, and so on. We have a data plane problem, which is combining the data at rest with the data in motion. And we need consistent feature engineering as well. Here is an example of a machine learning lifecycle. We go through use case definition, feature engineering, model training, evaluation, through operationalization. And this is typical, nothing. Here's an example of the machine learning pipeline at Comcast. So we have 3 main actors out here. We have the business user who defines the use case. We have the data scientist and the machine learning operations people. So the business user defines the use case. The data scientist then is going to explore the features, determine whether a feature exists. If needed, he or she will work with the machine learning operations people to create and publish new features. We'll validate the models. The models will go back to the business user for review. We'll go through an iterative process, finally go through model selection, and then model operationalization. We'll test those models in live mode to evaluate their performance. And finally, we go live with the model, and we establish a feedback loop. So again, going from answering questions to questioning answers, a reinforcement learning, making sure that you're making good predictions. So where does all this data come from? Where does all or some of this data come from? So we have 23 million TV subscribers, 26 million high-speed internet routers. We run our own network. We have lots of digital voice users and millions of Xfinity voice interactions every month. So every device is potentially a sensor, and they generate a lot of data together. So how do we bring all this data into our system? We have 600 Kafka topics and also a number of Kinesis streams, which generate billions of messages every day. And we use Apache Flink, Apache NiFi, and Spark streaming. So we use Apache Flink for the message processing, and also Apache NiFi as kind of the framework. So we take all the data from the streams, and we essentially build 2 types of feature stores, which are essential for machine learning. One is an online feature store. Think of it as a key value store. So the online feature store is the key value store used for the prediction phase. It needs to support fast ingest and query times because it stores the current data, right? The features are also written to a historical feature store where, which could be on HDFS or S3. Think of it as a Hive partition table. That's your long-term history. The data scientists will use the historical feature stores to essentially create their training data sets. And here is an example of the feature creation view. We have our Kafka topics and Kinesis streams. We use NiFi for workflow orchestration. We might have to do some real-time enrichment, so NiFi workflow might have to reach out to an external REST endpoint to get some other device telemetry, and we essentially pass that to another Kafka topic or stream to the online or historical feature store writer to save that data either in the online feature store, which could be, DynamoDB or Cassandra or MongoDB or Couchbase, or land it into one of our data lakes. And we have multiple data lakes, but we're primarily on using Hortonworks. We also write the feature metadata. So we've come up with two abstractions for our features. They could be the continuous aggregations on streaming data or the on-demand features. So the continuous aggregations on streaming data could be the number of times a customer has called in the last 30 days, and that's an important metric, or the number of signal errors which a device has come up in the last 24-hour period, and so on. And the on-demand feature could be the diagnostic telemetry real-time from a device. And we do it only if needed, because sometimes they're expensive to collect. Sometimes we need to take the permission of the customer before we collect it. And the main distinction is in the on-demand features, we also enrich it with a time to live, which the model metadata can use. We collect it, we store it. The model during runtime is going to determine whether it can use that particular feature. Let's say if it's 24 hours old, so can it use it, or does it need to recollect the feature? Here's an example of using the online feature store. We have the Kafka, the Kinesis queue. The payload just contains the model name and the account number. We're going to dip into the model metadata, which we call feature assembly, find out what features are needed for a particular model. We pull the required features by account number from the online feature store. And we pass the enriched features to model execution for predictions. So feature store, it's a standardized approach for defining data transformations. The key message I wanted to get out here is the transformation definition is separated from the context in which it's applied. So we want to make our features reusable. And here are some of the details, the metadata related to features that you might want to capture. You have a namespace, name schema, a feature version, a list of partitions for the feature is something which is used in the historical features. And then similarly, we have the model store. And you have the model metadata. So consistent feature engineering is important. We want to make sure that We use the same kind of feature attributes which we use during the training phase are used in the prediction phase as well during actual runs. So everything is metadata driven. Okay. Here's a final run through of what's happening during the actual prediction phase. You have the model feature metadata stores and the online feature store. We get the payload, which is the name and the account number. We do feature assembly, which is using the feature store API to find out the feature metadata, finding out what features need to be assembled from the online feature store. We go through a decision process. Are all features current? Let's say they are not. And we would get the actual features from either the online or historical feature store, do a feature assembly, and finally our prediction. We also write the predictions that we made to the prediction historical store so we can go back and review how well the models are working. And just a little bit about Presto. We have the data plane issue, and we have discordant data sources. And Presto has been very, very useful for us. Presto allows us to query the data wherever it lives. It's a distributed SQL query engine for big data. It was something which was open sourced by Facebook. Yesterday, in one of the keynote presentations, somebody said that we will soon come to a day where every device we will be able to run SQL against it. And if there is anything which comes close to that promise, that is Presto. It's highly performant. It allows querying data where it lives. It has a connector architecture. It's very well suited for low latency interactive data exploration. And one strong testament to Presto is Amazon's Athena serverless query infrastructure is also based on Presto underneath the covers. So we use Presto to corral everything. So we don't usually have the liberty to make lots and lots of copies of the data. So Presto allows us to query the data where it lives. It even allows distributed queries across systems. So some of the lessons that learned for a successful machine learning pipeline, these are just thoughts, and you might have seen them. Is coming up with features is difficult, time consuming, and requires expert knowledge. Applied machine learning is basically feature engineering. That's coming from Professor Andrew, and he's a very well-known entity when it comes to kind of machine learning and data science. Feature engineering is an art. Most of the success of machine learning is in engineering features that a learner can understand. And metadata is important. Tribal knowledge does not scale. You need a data catalog of things. So I'm going to pass it back to Ray.
Thanks, Prashant. I think I've got like a minute. Basically, you've heard a lot of great stories. Metadata is very, very important. Our next, goal here in the next quarter or two is to sort of finish work on an API-centric set of approaches. Rather, we're really script-based right now. We're very focused on we're still kind of manual, I guess is the best way to say it. So become API-driven, promote reusability through a portal that helps people share stuff. Let me just sort of take you through a little bit about where we are. We have a portal in place right now that uses Atlas as a backend that lets us search for data. So data, getting a handle around the data is something that we're doing pretty well. Or starting to do well. gives you an example of where things are, what the database is, what the platform is that they're, so that could be an internal or external data source. We have many different platforms that use it. We have data offerings, which are, which will drill down into the data sources that you just saw. So we have a lot of information about that. So we're, again, collecting all of that metadata. Physical objects associated with those. Again, this, really useful stuff at least for those in the know. And, again, more information about the data offerings. So really good stuff that are helping people today. Kind of where we're taking this in Q3 2018. More, again, APIs with Python and Scala. OpenML.org is really driving a lot of some of the visualization work that we're doing. Uber has done a lot for us in terms of their Michelangelo product is sort of driving what we do. We want a common production environment, so containerization, right, to run Spark or H2O scoring models or others. Similar to SageMaker, but we have an ecosystem that's both Amazon and internal, and open sourcing a lot of what we do. Just a quick run through of sort of the data science portal. We'll have information about the data sets we're working with, the features, training runs, published models, and many other things. This is just an initial hit of that. And again, information about the features, quality values about the features, and other things that we can do as well. So that was a quick run through, was it not? GitHub, check out some stuff that Comcast has put out there. We're doing a lot more. We do a lot with Apache Atlas. We've done a lot of work with Dr. Elephant, more specifically with Tez. Do a lot of work with Accumulo. So look for us in those projects and other projects too. And I don't even think we have time for questions, but I don't know, do we? None. But see us afterwards. We're happy to answer questions. And thank you very much.